Hello everyone, I'm Hina Chandak, one of the TAs for the Introduction to Deep Learning course. So, welcome to the part 3 of the Numpy recitation series. In this recitation, we are going to be looking at how we can use Numpy to combine data and perform some basic math operation. So first, we're going to be looking at concatenation. So what you do in concatenation is essentially you join two arrays along an existing axis, and this is valid only if both the arrays have the same shape, except of course in the concatenating dimension. So let's see an example. Suppose you have two arrays of the shape 3, 2, 2. And if you concatenate it along axis 0, then you're going to end up with a resultant concatenated array of the shape 6, 2, 2. And similarly, if you concatenate it along axis 1, you will end up with an array with the dimensions 3, 4, 2. And if you would have chosen axis 2, you would end up with an array with the dimensions 3, 2, 4. So the next type that we're going to be looking at is called as stacking. What stacking does is basically it joins two arrays and creates a new axis. So let us take a look at how this works. So suppose you have two one-dimensional arrays, and if you stack it along axis 0, then you will see a new stacked array that has a dimension of 2, 3. Similarly, if you would have stacked it along axis 1, then you would end up with the resultant stacked array with dimensions 3, 2. What is happening here is basically that it's retaining the number of rows and it just adds 2 columns. And if you add axis is equals to -1, it basically takes the last dimension. In this case, it's 1. So you get the same response in both these cases. Now, let us take an example where we will be using 3-dimensional arrays instead. So here, we have two arrays with dimensions 3, 4, 5. And if we stack it along axis 0, then we see that a new dimension is introduced. And then you're going to end up with a new stacked array with dimensions 2, 3, 4, 5. Had you chosen axis 1, you will end up with the resultant stacked array of dimensions 3, 2, 4, 5. And if it was axis 2, you would end up with this array having these dimensions. And if it was axis -1, you would end up with this. So now let us look at some common math operations that we are going to use Numpy for. So the first one that we'll be looking at is known as broadcasting. Let us say that you have two arrays of the shape 1, 3 and 4, 1. You can actually add these two arrays or multiply these two arrays. And although this is counterintuitive, Numpy does this thing in the back that is known as broadcasting, where it does an element-wise addition or multiplication. And what it's doing here is that, and it's going to then perform that particular function like addition or multiplication. So basically, it starts from the last dimension or the rightmost dimension, and if it checks if the dimension of the two arrays are equal or if one of them is a 1. So let us take a look at this example. So here, if you see in these two arrays, it's going to start from the last dimension and it's going to compare them. So it checks that one of them is a 1. So now, since this is 1, it's going to match the dimension of this particular array. And since here it's 3, this is going to expand as 4, 3, which means this column array will now this is going to repeat 3 times. And it's going to be 4, 3. And then it goes to the second dimension and it compares both of these. It sees that one of them is a 1. And since this is 1, it's going to expand this dimension to match the other dimension. And so now this also again becomes a 4, 3 array. And now it becomes a valid operation. Since both of these are 4, 3, you can now perform addition or subtraction or even multiplication. Now, let's take a look at few element-wise operations. So if you have two arrays of the shape 2, 3, and in this case, we can add a scalar which what it does is that it's going to basically add that scalar to all of the elements. Now you can also add both of these arrays, and you will see that it will perform element-wise addition. You can also multiply them, and even if you take a square root of this, it will take element-wise square root. Now let's take a look at reduction. In this case, you are essentially going to take an n-dimensional array and apply some function on it. And this will be reduced to one particular number or axis. So let's say you have a particular array which is of the shape 2, 3. And now if you do an np.max, it's going to find the maximum number across all the axes. And in this case, if you see here, it's going to return 0.97. You can also find the maximum value or the minimum value along a particular axis by giving the axis dimension. So you can go look through all the functions that we have specified here, go through the documentation and understand in more detail what they do and how they exactly compute these at a reduction level. So here we have used different axes, and we have also printed the results that it's going to print the maximum value index along a specified axis, and we can check all of these out. Finally, you have comparison, where this is the final one in the element-wise operation list. So suppose you have two arrays of the shape 2, 3. You can pretty much run any relation operator like greater than, lesser than, not equal to, and get the result which says where it is greater than, and so on. You can also check dot any or dot all, and this is also going to specify to you whether there exists any element that satisfies a condition or whether all the elements satisfy a condition. And they will also return Boolean values. You can also specify along the axis along which you want to test these, and you will correspondingly get results of that particular shape of the axis. You can again take a look at these examples and test them out. Now, let us take a look at few vector and matrix operations, basically matrix multiplications. So there are two ways that you can multiply two vectors or matrices. One is by calling np.matmul, and the other is by using the @ operator. Both of these work in the same way. So if you have to do a vector into a vector, a matrix into a vector, or a matrix into a matrix, as long as all your shapes follow the rules of matrix multiplications, all of these will be perfectly valid. So we are performing all of these here, and the results are also printed. There is also something called as dot product that is supported by using np dot dot. And you can basically perform matrix multiplication using np dot dot. And this is equivalent to using np dot matmul or @ for two-dimensional matrices. You can test all of these out in the notebook that will be shared with you. Now let's take a look at tensor dot. So tensor dot is actually a very important function, especially for homework too. Let's say you have two different arrays of shape 3, 4, 5, which is array A, and array B of the shape 4, 3, 2. So whenever you do tensor dot, you actually specify the axis along which you want to perform some reduction. So for A, we're going to specify 1, 0, and which in this case will be 4, 3, and for B it's 0, 1, which is again going to be 4, 3. So now if you look at the output of np.tensor dot, it's going to give you the resultant array with dimensions 5, 2. And that is because you have performed some reduction along axis 1, 0 and 0, 1. So you end up, which means that these axes have been collapsed, and what remains is basically 5, 2, which are essentially spread out. If you look at the equivalent code in Python, for np.tensor. It's essentially going to be implemented with 4 different for loops. And in order to exactly understand how this works, please do check out the link that is given in the notebook. And it is left as an exercise for you guys to try and figure out why these for loops change to particular numbers and why this formula works this way. Hope you guys found this recitation useful. Thank you for listening.